All right, so let's go over some practice problems from our textbook, starting with section 3.5, and this is going to close out chapter 3 for us. So with problem 8 here, we're told that Jessica enrolled in a course that promised to increase her reading speed. So to help judge the effectiveness of the course, Jessica measured the number of words per minute she could read prior to enrolling the course, and she obtained the following 5-number summary here. So we're going to use this information to draw a box plot of the reading speed. So the first thing to note here is that we're told that this is a 5-number summary. So that means that this is going to be our minimum value. This 140 is going to be our Q1 value. This guy is going to be our medium value, also known as Q2. We have Q3, and then we have our maximum value. So we're going to use this information to draw a box plot. First, we need to find our lower and upper fences. So our lower fence is going to be our Q1 value minus 1.5 times IQR. All right, now IQR is going to be the difference between our Q3 and Q1. So we're going to need to find that first. We also want to find our upper fence. So this is going to be Q3 plus 1.5 times this IQR value. So, like I said, IQR is going to be the difference between Q3 and Q1. So this is going to be 173 minus 140, which gives us 33. So now what we're going to do is we're going to plug in this 33 value into this IQR here, along with our Q1 and Q3 values. Doing so, we're going to have 140 minus 1.5 times 33 for our lower fence, which gives us 90.5. And doing the same thing for our upper fence here, we're going to have 173 plus this value, which gives us 222.5. All right, so with this information, we can draw our box plot. So let's do this on the side here. The first thing that we're going to want to do is draw a large number line that encloses all of our data points here. So let's start with 110 is going to be our minimum value on this number line. All right, let's increase in increments of 10. So we're going to have 120, 130, and so on. And we're kind of running out of room here. I'm going to put another tick mark and then just redraw this line. So we do want to include this maximum value of 205 here. So we're going to go up to 210. So this is our number line here. That's going to be our first step. Now our second step is we're going to be drawing lines along or vertical lines that match up with our Q1 and Q3 values, and then enclosing them in a box. So what I'm going to do is just draw a box there. So we have our 140 value, and then our 173 is right about there. So we have this box right here. Right, then the next thing we want to do is draw a vertical line to represent our median value, which is going to be 157. So that's going to be right about there. And then the last thing that we're going to do is draw our lines horizontal coming out of our box all the way up to our maximum value on the right here. So all the way up to about 205. And then also to our minimum value on the left side. So 110 here. And so these are called the whiskers of our box plot. And then we're going to title this box plot the reading speed. So that's what this data represents. All right, so that's how we would draw a box plot given that information. Now for this next problem, we're going to do something similar, but in this case, we're not actually given the 5-number summary. We would need to find that first. So the following data in this table represent the percentage of workers who carpool to work from the 50 states plus Washington, D.C. So note that the minimum observation of 7.2% corresponds to Maine and the maximum corresponds to Hawaii. So in this table here, notice that these guys are already in order here. So that's nice if we move in this direction here. Now we want to find the 5-number summary. So we're going to want to find our minimum value, which we actually can see is the 7.2 here. Our maximum value is the 16.4. So we already have two of our numbers. We just need to find our Q2, our median value, our Q1, and our Q3. So the first thing that we're going to want to find is our median value. All right, so notice that since these are already numbered in order in ascending order, we could just cross out one number from each side of this guy and meet in the middle. But an easier way to do that is to use this formula here. So the median is going to be the n plus 1 divided by 2 position in this table here. So n is going to be the number of observations that we have. If we count all of these guys, we're going to have 51 observations. So n is 51. We're going to add 1 to that and divide it by 2. Doing this, we're going to get the 26th position in this table here. So that means the 26th position is going to be our median value. And we can do this since we have an odd number of observations here. Now, just something to note here, if n is even, then the median is going to be the average of our values. Let's actually just write this here. So if n is even, so the median is going to be the average of the values in the n over 2 plus, or sorry, and the n over 2 plus 1 positions. Okay, so just something to note, if n is even, we do kind of the same thing, but instead of doing this n plus 1 over 2, we're trying to find the average of these two positions here and find the corresponding data value. So for this one, going back to this guy, the median is going to be in the 26th position here. So counting all of these positions, the 26th position is going to be this guy here. So that means the median is going to be 10. So M, which is the same thing as Q2, gives us 10. All right, now the next thing we want to do is we're going to find Q1. So Q1 is actually going to be the median of the first 25 values, right? We see that the 26th position is going to be the middle value for this entire data set. So now we need to find the middle of the first 25 values here. That'll give us Q1. And in fact, Q3 is then going to be the middle of these bottom 25 values here. So again, since we know that we have a odd number of values, we can use this formula. We have this n plus 1 over 2. And in this case, since we're only looking at the first 25 values in this data set here, we can kind of think of n as 25, just for this particular case when we're trying to find this Q1 in this example. So we're going to have 25 plus 1 over 2, which gives us the 13th position. So the value in the 13th position is going to be Q1. And let's just keep color coding. Doing that, we're going to get this 9 here. So that means Q1 was equal to 9. And then we said Q2 was 10 here. So we're going to do the same thing for Q3. So our third step here, Q3 is going to be the median of the last 25 values. All right, so this is going to be the 13th position after Q2 for the same reasoning that we saw here. If we're looking at the last 25 values, our sample is going to be 25. Adding 1 to that and dividing by 2, we're going to get the 13th position, but we just have to be careful with this. This is going to be the 13th position after the median or Q2. All right, so finding the 13th position after that, let's do this one in pink here. We are going to get this 11.2 here. So kind of running around the room here, Q3 is going to be 11.2. All right, so with this information here, we have our 5-number summary. So we'll write this on the side here. All right, so we're going to have our smallest value, which we know is 7.2 from our table here. Then we're going to have our Q1, which is going to be 9 or 9.0. Then our median value, our Q2, is going to be 10.0. Then we found that our Q3 was 11.2. And then going back to the table for our last value, our maximum value, that's going to be 16.4. All right, so that's how we would find the 5 number summary for this data set. All right, so for part B of this example, we want to construct a box plot using this 5 number summary here. So we're going to do so just like we saw in the first example for this section. We first need to find our lower and upper fences. So our lower fence is going to be Q1 minus 1.5 times our IQR value. Our upper fence is going to be our Q3 value plus 1.5 times IQR. Now, first we need to find IQR, which we know is going to be the difference between these guys, and is going to be 2.2. So if we were to plug in our Q1 and 2.2 values into this, and then Q3 and 2.2 into this guy, we would get 5.7 and 14.5. All right, so with this information, we can start constructing our box plot. So first, we're going to draw a number line here, which encloses all of our values from our minimum to our maximum value. So I'm going to start at 6 here since our minimum value is 7.2 and increase in increments of 2. We're going to go up to 16 here. Our maximum value was 16.4 in this case. All right, so the first thing we're going to do is draw vertical lines at our Q1 and Q3 values and then enclose them in our box. So a vertical line here, and I'm just going to go ahead and draw the box like this. We have our vertical line at 9. Maybe I'll move this over slightly. And then we're going to have our other vertical line at about 11.2 here, and then we're enclosing it in a box. The next thing we want to do is draw a vertical line at our median value, so that's going to be 10 here. All right, now we need to draw our whiskers. These are going to be the horizontal lines coming out of our box plot. Now, this is where our lower and upper fences come into play. And in the last example, we actually didn't go into too much detail with them. Let's actually scroll up to this last example here. So in this case, these whiskers go from our box here all the way up to our maximum value. And in this case, they go from the left of this box all the way to our minimum value. And the reason why our lower and upper fences didn't play a role in this case is because they're smaller than our minimum and maximum value. So what we're going to do if that's the case, if our minimum value is bigger than our lower fence, we're just going to go up to that minimum value. And if our upper fence is bigger than our maximum value, we're just going to go right up to that guy because these minimum and maximum values are kind of enclosed in these fences and these boundaries here. Now going back to this example, notice that our minimum value is enclosed in this lower fence. We're saying our kind of like interval here, our lower fence is going to be this 5.7. That's kind of like our boundary. And our minimum value is enclosed in that. So we're just going to draw a whisker from this left-hand side of our block of our box up to our minimum value of about 7.2 there. However, on the right-hand side here, we know that our maximum value is 16.4. So you might want to draw a whisker from this guy all the way to 16.4. But remember, our upper fence is this 14.5 here. So that means that the 16.4, our maximum value, is actually outside of our upper fence. And so it's going to be an outlier. So when this happens, we're going to draw this whisker all the way up to our upper fence there, about 14.5-ish. And then we're just going to draw a little asterisk to represent 16.4. This is going to be our outlier. So this is what our box plot would look like. And let's title it. I'm going to call this percent of carpoolers. That's what we're looking at in this example. All right. Now, the last thing for part C here, we want to comment on the shape of the distribution. Now, Notice that our whisker on the right side, this right line is longer than the one on the left, and we also have an outlier on this right side. So that means this distribution is skewed right. So I'll say this distribution is skewed right. Um, we'll say the right whisker, it's not how you spell whisker, longer than the left, and we have an outlier on the right side. So this guy, this distribution is skewed to the right. All right, so this brings us to section 4.1. For this first example, we're given a set of data, and we first want to draw a scatter diagram of this data and then compute the correlation coefficient by hand. So let's start with part A here. We want to draw a scatter diagram. And notice we have our x and y variables here. So all of these x variables are going to be on our horizontal axis, and then y is on our vertical. So we have our vertical axis y, and then our horizontal x. Move this over there. All right, now let's increase in increments of 2 on the vertical axis here. And we're going to go up to, let's just go up to 12. And then on the horizontal axis, we're going to increase in increments of 2 as well, but we're only going to go up to 8. This is going to be 6. And then we'll have 8 here. All right, so now we're just going to plot these guys. Our first point is going to be 2 comma 10. So when our x value is 2, our y value is 10. So we're going to put a point here. Next, we have 3 comma 9. So 3 is right about here and 9 is right about there. So 3 comma 9. The next one is 5 comma 7. So we have 5 and we have 7 is going to be maybe right around there. Then we're going to have 6 comma 4, just goes here. And then we have another 6 comma 2. So we're going to have a point there. So that is what the scatter diagram of this data would look like. Now for part B, computing the correlation coefficient by hand is going to be a little bit of work here. The formula for this guy, so R is going to be the correlation coefficient. And to find it, we're going to have to do some work. So we want to take the sum of all of our x sub i's here, all of our data points, and subtract out the mean of these guys, and then divide this whole thing by the standard deviation of our x values here. And then we're going to multiply this by the same thing for our y values. And so we're going to take the sum of this product here. Then we're going to divide this entire thing by the number of values minus 1. Okay, so in order to do this, we're going to need to find some values. Just like we saw in the last video, we should be comfortable computing the mean and standard deviation, so we're not going to go through the process of that. I'm going to tell you what they are. Our mean for our x values, so we're going to add these guys up and then divide by 5, is going to give us 4.4. And then the standard deviation, which we denote as s sub x here, is going to be this. This is a 5, 6, 9, and we're going to do the same thing for our y values. We're going to get 6.4 for the mean, and then our standard deviation is going to be this. Okay, so the next thing that we want to do is find these values. And in order to do that, we are going to construct a table like we've seen in the last videos, and then plug in our sum for all of these values into this formula. So constructing our table, the first thing we're going to need to do is organize all of our data points here. So we're going to have our x and our y values. Then what we can do with this information and our mean and standard deviations for both is we can compute these guys. So the next column, we're going to have all of these values. And the next one, we'll have these values. And lastly, remember we're trying to find the sum of the product of these two. So naturally, we're going to need to find the product of these guys. And then we can add them all together to get this value in the numerator of this formula. All right, so that is going to be our table here. So we want to fill in these values. We know all of our x values. We have 2, 3, 5, 6, 6. All of our y values are 10, 9, 7, 4, and 2. All right, and I'm actually going to, let's maybe make some more room. Let's move this over. I want to maybe do a few calculations just to show you guys how we're getting these values. Alrighty. So the first thing that we want to find is this guy. So we're gonna plug all of our information into this formula. First, we're gonna put this 2 here, and then we're gonna subtract out the mean of this guy, which is 4.4. And then we're gonna divide by the standard deviation, this 1.81569. This is gonna give us negative 1.32116. Okay. We're gonna do the same thing for this guy. We're going to plug in our y value, which is going to be 10, subtract out the mean for our y values, which is 6.4, and divide by the standard deviation. Doing so, we're going to get 1.07093. Lastly, to find the product of these guys, we're just going to multiply what we got in the first two columns. So we have this negative 1.32116. We're going to multiply it by 1.07093. This will give us negative 1.41487. So what we're going to do is do this for every single x and y value and fill out this table. So I'm going to go ahead and do that, and I'll be right back. All right, so here is the completed table, just repeating this process that we saw for the remaining x and y values. Now, the value that we're really concerned with is the sum of the products of these guys. So we found all of the products and we added them together, and we're going to get this value. So we're going to plug this value directly into this formula here. So this will become the numerator of this guy. So we're going to have negative 3.73369 in the numerator. In the denominator, we're going to have n minus 1. We know we have 5 points here, so this would be 5 minus 1, which gives us 4. So plugging this into our calculator, this is going to be roughly negative 0.933. So that is how we would find the correlation coefficient by hand. So for this next example, we are looking at credit scores. So we all know that your FICO credit score is used to determine your credit worthiness. So it's used to help to determine whether you qualify for a mortgage, a car loan, and it's even used to determine insurance rates. So FICO scores have a range of 300 to 850, with a higher score indicating a better credit history. So the given data in this table here represent the interest rate in percentage a bank would offer on a 36-month auto loan for various FICO scores. So for example, if your credit score is 545, you're going to get about a 19% interest rate and so on. The better your credit score, the better your interest rate. So for part A, which variable do you believe is the explanatory variable and which is the response variable? So the response variable is going to depend on the explanatory variable, right? So your interest rate depends on your credit score. So this means your explanatory variable, which I'm going to abbreviate with the EB, is going to be your credit score. And then the response variable, RV, depends on the explanatory variable. So your interest rate depends on what your credit score is. All right. Now for part B, we want to draw a scatter diagram of this data. So we know that, let's put it in this corner here. We know that on our vertical axis is going to be our response variable. So this is going to be our interest rate. And then our horizontal axis, this is going to be our explanatory variable. Let's make sure this is lined up nicely. So we're going to have our interest rate here. And our units, this is a percentage here, and then our credit score. So our range is from, we're going to do 550 to 750 here, and we'll increase in increments of 50. So starting at 550, 600, and so on. And then on our vertical axis here, we have our interest rate. Our lowest one is 5%, and our highest is almost 19. So let's start at 5%, and let's increase in 2.5%. So we're going to go to 7.5, then we'll do 10, 12.5, and then so on. So we'll go right up to 20. All right, so now we just need to plot this data. So our first point is going to be 545 and then about 19% here. So we'll go maybe right around here. This is a rough estimate, it doesn't have to be perfect. Our next one is almost 600, 595, and then about 18%. So maybe here, our next one, 640 and 12%. 675 and almost 9%. Maybe right around there. 705 and about 6.5%. Maybe right around there. And then lastly, 750 and a little over 5%. All right, so that's what our scatter diagram would look like. Now for part C of the same problem, we want to determine the linear correlation coefficient between the FICO score and interest rate on a 36-month auto loan. So again, we're trying to find this R value, which we saw in the last example can be a little complicated. So I've already set up this table for us. We also know that we need to find the mean and standard deviations for both variables separately. So let's put this information here on the side. Our mean is going to be this guy. Our standard deviation is this here for our X variable. So that would be our credit score. And then for our interest rates, this is the mean. And then our standard deviation is going to be this guy. All right. Now we're just going to input our X and Y variables. We have our credit score starting at 545 and ending at 750. So these are going to be all of our X variables. And then our Y variables, putting that in the table, is going to be all of these guys. So I'm going to go ahead and fill in this table just like I did in the last example, and then come back to find this correlation coefficient. All right, so we have this table filled in. We put our credit scores and our interest rates here. Then we found these values by plugging in the corresponding X values. So for this one, we plugged in 545. We subtracted out this mean here, and then we divided by the standard deviation, this guy here. Repeating this process for all of these guys and the Y variables. We then multiplied these guys together to get this, repeated that for the rest of these ones, and then took the sum of these products. This sum is going to be this negative 4.87936. So that's what's going to go in the numerator of this guy. So in our denominator here, this is going to be our sample minus 1. We have 6 points for this. So 6 minus 1 gives us 5. And so this is going to be approximately negative 0.976. So this is going to be our correlation coefficient for this guy. Now, the last part of this question here asks, does a linear relation exist between the FICO score and the interest rate? So in order to determine that, we're going to need to look at the critical values for our correlation coefficient. So if you remember from the textbook here, I'll write this little blurb. If the absolute value of our correlation coefficient is greater than the critical value, which we can find in this table here, there is a linear relation between the two variables. All right, so in this case, we need to find the critical value. So we know our n is 6. So our corresponding critical value is going to be this 0.811. And if you remember going back up here, our correlation coefficient was this guy. So in this case, yes, there is going to be a linear relation between the FICO score and the interest rate, because if we take the absolute value of our correlation coefficient, this is going to be greater than this critical value. So in this case, since it is greater than this guy, we're also going to say that there is, or sorry, since our correlation coefficient is negative here, we're going to say that there is a linear relation, but there's going to be a negative association. All right, and then something to note here, we'll put a little asterisk. So if our correlation coefficient R is positive, then there's going to be a positive association. All right, so that concludes that exam. All right, so this brings us to section 4.2, question 10 here. So for the data and in this table, we're going to be answering a bunch of different questions. The first being, we're going to draw a scatter diagram treating x as the explanatory variable and then y as the response variable. So let's do that in the corner here. And we should be pretty comfortable drawing our scatter diagrams by now. We know that our response variable is going to be on this vertical axis. This is going to be y, and then our explanatory variable x is going to be on the horizontal axis. Now, in this case, we do have some negative values for x. So on our number line here, we're going to be including some negative and positive values. So this is going to be treated as our origin here. This is going to be 0. And we're going to have -1 and -2, and then +1 and +2 on this x-axis. And then on our vertical axis, our y-axis, we are going to start at 2 here, and then we'll increase in increments of 2. So 2, 4, 6, and then we're just going to go up to 8 here since our largest value in this data set is 7. So we're just going to draw this scatter plot. Our first point is going to be -2, 7. So looking at this -2 here on our x-axis, we're going to go up to 7. So somewhere around here. Our next point is -1, 6. So that'll be around here. Then we have 0, 3. So that means for our x-axis, we're not going to be moving anywhere. We have 0. But then for our y-axis, we have 3. So we're moving up 3 right on this vertical axis here. Then our next point is 1, 2. So we're moving over 1 in the positive direction here and then going up 2. And lastly, we have 2, 0. So on the x-axis, we're going to be moving 2 units here, but we're not going to be moving in the vertical direction at all since this y value is 0. So we're just going to be right here on our x-axis. Now let's see what we have for part B. For part B, we're going to select 2 points from the scatter diagram and find the equation of the line containing those points selected. So this is definitely going to be dependent on which points that you pick. So let's do part B right next to the diagram here. I'm going to pick some points. I'm going to pick kind of nice, easy points here. I'm going to pick 0, 3 and 1, 2. All right, so now we want to find the slope and then use that to find the equation of the line containing these 2 points. So we know the slope is going to be, this is going to be y2 minus y1 over x2 minus x1, where these are x1, y1, and then x2, y2. That's how I'm going to label these guys. Okay, so this is our first x coordinate, our first y coordinate, and so on. So y2 is going to be 2, y1 is going to be 3. In the denominator, we have x2, which is 1 minus x1, which is 0. So this is going to be a -1 in the numerator and then a 1 in the denominator, which just gives us a -1. So this is our slope. And we want to write an equation in this form of y is equal to mx plus b here. I'm going to write this. There we go. So y is equal to mx plus b, where m is going to be our slope, this -1, and then b is going to be our y-intercept. And actually, our y-intercept occurs when x is 0. So this b value is going to be what we have here, this 3. So plugging this information into this form, we're going to have y is equal to our slope, which is -1. So I'm just going to write this as a negative here. We don't have to necessarily keep that 1 there. It's just going to be -1 times x, which just gives us -x. And then plus b, and in this case, b is going to be 3. So this is the equation for our line. And then in part C, I think we're graphing this. Let's see. So we're going to graph the line found in part B on this scatter diagram. So instead of drawing another one, I'm just going to color coordinate. So for part C here, we're graphing this blue line. Okay, so in this case, we know what our y-intercept is, so that's where we're going to start. Our y-intercept is 0, 3. So I'm going to plot that on this diagram here. It's going to be this point. Now our slope is -1, so our line is going to be in this direction. And so what we're going to do is just go up 1 over 1. Going left 1 gives us this negative. And in this direction, we're going to go down 1, which gives us that negative, and then over 1. So if we go up 1 over 1, this is going to be 4 and then -1. And then if we go down 1 over 1, we're going to have this point here. So for to graph this line, it's going to look something like that there. All right. Now, for part D, what we're going to do is determine the least squares regression line. So this is the line that best describes the relation between our two variables. And let's do that down here. So for part D, we want to find this least squares regression line. Now that is given by this y hat here, and it's equal to b1 times x plus this b naught, where our values for b1 is going to be this correlation coefficient r times our standard deviation with respect to our x variable divided by our standard deviation with respect to our y. I'm actually going to write this subscripts a little bit smaller so it's clear. Okay, and then our b naught value is going to be this guy. So the mean for our y variables minus b1 times the mean for our x's. All right, so in this case, I'm going to give you some of this information. We know how to find the mean values, we know how to find the standard deviation, and we know how to find R from the last section. So I'm just going to give you these values and we can plug them in. So the mean for our x variables, we're just going to add these guys together and divide by 5. That's actually going to give us 0. Our standard deviation, this x sub x here is going to be rounded approximately 1.58114. Our mean for our y variables is 3.6. And then the standard deviation is again rounded to this guy. Okay. And then lastly, our correlation coefficient. We're not going to go through the whole process of finding that again, but it's going to be negative 0.98788. So with this information, we are going to plug this into our B1 and B naught values and find this, what we're going to call y hat here, or the least squares regression line. So first, let's find B1. This is going to be our R value times this fraction here, our ratio of our standard deviation with respect to x over the standard deviation with respect to y. This is going to give us approximately negative 1.8. Then for B naught, again, we're just plugging in these values. This is going to be our mean value for y, so 3.6, and we're going to subtract out this B1 times the mean for our x variables, which is going to be 0. So we're multiplying this by 0 here. And I'm just putting these parentheses here to emphasize that we're subtracting out a negative. So it is usually nice to put parentheses here. We don't want to drop any signs or anything. But luckily in this case, since we're multiplying by a 0, this whole thing's going to go away. So our B naught is just going to be 3.6. So plugging this in to our equation for the least squares regression line, we're going to have B1, which we know is negative 1.8 x plus our B naught value, which we found to be 3.6. So this is our least squares regression line, and we're going to do that in green here. Now for part E, we're actually going to graph the least squares regression line on the scatter diagram. So just to keep color coding, we're doing A, C, and E on this one scatter diagram, so we don't have to keep drawing them. So going back to our equation for our least squares here, we know that our y-intercept is going to be this 3.6. So we'll graph this point right here on this diagram. And then our slope is negative 1.8. So again, we are going to have a line in this direction, which makes sense. Remember, it is going to be the line that best describes the relation here. So what we're going to do in this case is we're going to go up 1.8 and then to the left one to correspond for that, or to take care of that negative. And then we're going to go down 1.8 and then to the right one to take care of that negative in this direction. So let's see, if we were to go in this direction here, we're going to go up 1.8. So that would be about 5.4 here. And then we're going to go to the left one. So maybe right around there. And then for this one, starting in this point here, we're going to go down 1.8 into the right one. So going down 1.8 from this point here. So we're going down 1.8 from 3.6 is going to be 1.8. So down 1.8 gives us this point, and then we're moving over 1. So somewhere around there, connecting the dots gives us this line. Now, for the last two parts in this problem here, so for part F, we're going to compute the sum of the squared residuals for the line found in part B, so this guy. And then for part G, we're going to do the same thing, except we're going to compute the sum of these squared residuals for the least squares regression line found in part D here. Yep, so let's do F. We are trying to find this residual, which is going to be y minus this y hat here. But in this case, we're working with this guy. So per usual, we are going to set up a table. We're going to have our x and y values here. Then we're going to put this y hat here. So this is going to be like our residual value. Let's write this here, is going to be our observed value minus our predicted value. So for example, if x is -2, our observed value is 7. But then this y hat here is going to be what's predicted based off of this equation that we found. So, and then what we want to find is this residual and then square it. So that'll be the last column here. So let's input our x and y values. When we get -2, we're going to get 7. -1 gives us a 6. 0 is a 3. 1's a 2. And then 2 gives us a 0. So this is our observed y values. And then to find our predicted y values, we're going to plug in this x into this equation and see what we get for y. So if I were to plug in a -2 into this guy here, I'm going to get a negative times a negative, which gives us a positive, and we're going to get 2 plus 3. So this will give us a 5. So that means the difference between our observed value of 7 and our predicted value of 5 is 2. And then we're just going to square it. Okay, so repeating this process, We get all of these values. So just filled everything in, doing exactly what we did for this first row here. So we found these guys here, the square of our residuals, and we want to find the sum of them. So the sum of these guys is just going to be adding these guys together, which gives us 9. Now for part G, we're going to do the same thing, except now we're working with the least squares equation here. So again, we have our x and y's, but instead of this equation, we're going to have this guy. So let's set up our table. So we have all of our x and y values here, and we want to see what we get for our least squares regression line. So we're going to plug in a -2 into, sorry, this should be -1.8 times x. That's our equation there, plus 3.6. So we're going to plug -2 into this x value. This gives us 7.2. And then the difference between our observed and our predicted value is then just going to be the difference of these guys, which gives us 0.2. And squaring that, we get 0.4. Okay, so we're going to repeat this process for the rest of our x's. All right, so filling out the rest of this table, we're going to get that the sum of the squares of our residual is going to be 0.8. Now that's nice. That's a really small value. So this tells us since the regression line has a smaller sum of these squared residuals, it has a better fit, which is to be expected. If you remember, the line that best describes this relation is going to be the least squares regression line. So we'll say that here. So the regression line has a smaller sum of squared residuals, so it has a better fit. All right, so in this next problem here, we're told that the data in this table represent the maximum wind speed and atmospheric pressure for a random sample of hurricanes that originated in the Atlantic Ocean. So for part A, we're going to treat atmospheric pressure as the explanatory variable, and the least squares regression line is given by this here. And what we want to do is interpret this slope. So our slope is going to be this -1.1994 here. And remember, slope is going to be our rate of change. It tells us how um, how our explanatory variable affects our response variable. So in this case, our explanatory variable is atmospheric pressure. So this tells us that for every 1 unit of increase in our atmospheric pressure, the corresponding response variable, this wind speed, is going to be decreased by a factor of this 1.994. So if x were 1, it's going to decrease by 1 factor of this guy. If x were 2, it's going to decrease by 2 factors, and so on. And this decrease here is indicated by this minus sign. So let's write a little sentence explaining that. So if the atmospheric pressure, I'm going to abbreviate that as atmo. If the atmospheric pressure increases by 1 unit, and in this case, that unit is going to be MB, which is millibars. So if the atmospheric pressure increases by 1 millibar, which we're calling MB, the response variable, the wind speed, is decreasing by this slope here. And in this case, our units for the wind speed is knots. And this is, we're going to say on average, since remember, this is our least squares regression line. So this is just the best fit for this data. All right, let's move on to part B here. So is it reasonable to interpret the y-intercept? Why? So in some cases, it might not be reasonable in the context of the problem to interpret the y-intercept. And in this case, it is not reasonable to do so. And the reason being is that, remember, our y-intercept occurs when our explanatory variable, our x value, is 0. And remember, our X value is the atmospheric pressure. So it doesn't make sense for the atmospheric pressure to ever be 0 millibars. It's going to be outside of the scope of the model, and I don't think we ever actually see it in the natural world either. So we're going to say, no, it's not reasonable to interpret the y-intercept because the y-intercept, which I'm going to abbreviate like this here, occurs when the atmospheric pressure is 0 millibars. And we're going to say, which is outside the scope of the model here. All right. And then lastly, for part C, one hurricane has an atmospheric pressure of 997 millibars. Is this hurricane's wind speed above or below average for a hurricane with this level of atmospheric pressure? So what we're going to do in this case is we are going to find the residual. So the first thing we need to do is plug in this 997 millibars into our equation given in part A. So we're going to plug 997 into this X value here. And then we are adding this to it. This is part of the equation. Doing so, this is going to be approximately 50.1387. Then our residual going to be our observed value minus our predicted value that we just found. And we can find our observed value in this table here. We're going to look at 997 millibars. The corresponding wind speed is 45. So our Y value that we actually observed was 45, and our predicted was this 50.1387. Subtracting this, getting our residual is minus 5.1387. So the wind speed is going to be below average for a hurricane with this level of atmospheric pressure. So we'll say that here. The wind speed is below average. All right, so this brings us to section 4.3. Question 6 here. So as concrete cures, it gains strength. The following data in this table represent the 7-day and 28-day strength in pounds per square inch of a certain type of concrete. So the coefficient of determination is 57.5%, and we just want to provide an interpretation of this value. So if you remember from the textbook and from the PowerPoint slides, the coefficient of determination is given by capital R squared, and it measures the proportion of total variation in the response variable, and it's explained by the least squares regression line that we saw in the last section. So essentially, this tells us how well the least squares regression line fits the data. So I'll say that here tells us how well the least squares regression line fits the data. All right. So in this case, this question is actually fairly easy. This just means that 57.5% of the variability in the response variable is explained by this least squares regression line. So we'll write that here. This means this 57.5% of the variability in the response variable is explained by the least squares regression line. All right, so that's it for this question. We just wanted an interpretation of that value there. Now, for the next example in this section, we're going to be working off of a problem from section 4.2 and from 4.1. So we have this table here, which represents the total length and weight of bears. So for this particular problem, we want to suppose that we find another bear that is 205 centimeters long and weighs 187 kilograms, and we're going to add this information to this original data set from problem 20, section 4.2. So with this new information, we want to compute the coefficient of determination of this expanded data set. And we're given some information that we've seen in previous sections. Um, we're given that the correlation coefficient, this lowercase r, is given by this here, and the coefficient of determination is given by this. And we find this coefficient of determination by simply squaring this correlation coefficient. So once we add this information to this original data set, what we want to do is find the new coefficient of determination and determine what effect this additional bear has on that guy. So what we're going to do first is we're going to add this information to this data set here. So we found another bear that was 205 centimeters and weighed 187 kilograms. So scrolling down here, I've written down the formula for our correlation coefficient, this lowercase r. This isn't the same formula that we saw in section 4.1, but it's equivalent. You'll get the same answer. In this case, we don't have to use our standard deviation. So just like we've seen in past problems, what we're going to want to do is find all of these individual values and then just plug them into this formula. So first, let's list out these values. We know our sample size is 13. We have 13 bears. We're also going to want to find the sum of all of our x and y values. We're going to add all of these guys together and all of these guys. So the sum of all of our x values is going to give us this. And then the sum of all of our y values is this here. Now we also want to find the sum of all these x values squared and same for our y values. So we're going to take the square of each of these guys and then add them together. Doing so for the length for our x values, we're going to get this here. And then for our y values, we have. And then lastly, we also want to take the sum of the product of these guys. Let's see, yeah, this one here. So we want to take the sum of the product of these. So multiplying each of these guys together and then adding each one of those up. So the sum of the product of our x and y variables is going to give us this. All right, so with this information, we can plug everything directly into this formula. Focusing just on the numerator, we're going to take the sum of the product of our x and y's. So that's going to be that 211 value there. Then we're going to subtract out the product of their sums. So we're going to take the sum of the x's and multiply by the sum of our y's. And then we're going to divide everything by our sample size, which is 13. Now in the numerator here, we're going to take the square root of this whole thing here. So we're going to have a square root, and our first guy is going to be the sum of these squared. So that's going to be the 288,000. And then we are going to be subtracting out the sum of these x values, squaring that, and then dividing that value by our sample size. So the sum of our x's is this guy here, and then we're squaring it and then dividing that by our sample size. And we're going to multiply this by the sum of our y's squared, which was this here, which we got from up here. Then we're going to subtract out the sum of those y's, square that, and then divide by the sample size. So what we're doing is we're multiplying these two values together, and then we're taking the square root of it. Okay? So a lot of complicated calculations here. Make sure you do it slowly. This is going to give us approximately 0.847. So this is our correlation coefficient, and we know our coefficient of determination is this r squared, and we can find that by squaring this lowercase r. So this would give us 0.847 squared, which is approximately 0.717, which gives us 71.7%. Okay. So this is our coefficient of determination when we add another bear to the sample. And we want to figure out what effect this new bear had. Well, remember our previous coefficient of determination, this r squared, was 49.5. And our new one is the 71.7%. So taking the difference of that is about 22%. So this tells us that adding the new bear increases the amount of variability by about 22%. So just taking the difference of our new r squared and the previous one. Moving on to section 4.4, we're looking at question 9 here. So a college education is a factor in determining one's income. Researchers at payscale.com wanted to determine if there's an association between mid-career income and household income while someone was in college. So the idea was to determine if individuals from low-income households earned a lower mid-career income than those from high-income households. So researchers surveyed 725 individuals in the middle of their careers and asked them to disclose their income class while in college and their current income. So the data is based on this results here. So this is what's called a contingency table, which relates two categories of data. We have our household income in college and then current mid-career income. So for part A, we want to construct a frequency marginal distribution. So to do so, we're going to take the totals of each row and each column. So actually, I took a screenshot of this table here, and I'm just going to paste it here so that I don't have to create a whole new table. Perfect. So we just need to find the totals of each row and each column, like I said. So the totals for each of these columns here, we're just going to add these guys together. This is going to give me 174. Then for the next column, 187, 173, and then 191. Now we want to do the same thing for each row here. So we'll say these are the totals. We're going to add these guys together. This will give us 220. For the second row, we'll have 290. And for the last, adding these guys together gives us 215. And then the sum of these, all of these rows and all of these columns here is the total amount of people surveyed, the 725. Now, this will be our frequency marginal distribution. And then for part B, we want to construct a relative frequency marginal distribution. So we're going to identify these, find these frequencies and compare it to the amount of individuals surveyed. So again, let's just paste that table there. And we want to find the relative frequency. So for all of these columns here, our relative frequency is going to be the total relative to the amount of people surveyed. So this is going to give us 0.240 for the first column. We're going to repeat this process for everything, all of these columns here. We're going to take the total for this 187 and divide it by the 725. This will give us 0.258. For the next column, we're going to get 0.239, and for the last, 0.2634. We're going to do the same thing for all of our rows here. We know the sum of all of these guys is going to be 220 from part A. This is going to give us 0.303. Repeating this for the next two rows gives us 0.4 and then 0.297. And then for this last guy here, the sum of this and this is going to give us 1. This is going to be the 725 divided by our 725 individuals. Now for part C, what proportion of households are in the second quartile and mid-career? So we're going to go back up to this guy. We're looking at mid-career second quartile. So this is going to be 0.258 for part C. All right. Now for part D, we want to construct a conditional distribution by household income in college. So a conditional distribution is going to list the relative frequency of each category of our response variable given a specific value of our explanatory variable. So what we're going to do in this case is we're going to determine the relative frequency for each household income in college. And dividing that by each frequency of the row total for our mid-career income quartiles. So that was a lot of words, but let's again paste this table here and go ahead and do that. So what we need to do for each of these is we're going to divide this guy by the row total. So going back up to this one, we know the row total was 220. So we're going to divide this 72 by 220. This will give us 0.327. Okay, we're going to do the same thing for all of these. Divide by 220, which gives us 0.282. And then we'll do the same thing for the third and top quartiles. Then for the second row here, we are going to divide each of these by the sum of the second row determined in part A, so 290. So we're going to divide each of these guys by 290. This one gives us 0.241. And then lastly, we'll divide each of these guys by the sum for this row, which was 215. All right, so I'm going to go ahead and fill that in. So filling in the rest of this table here gives us the conditional distribution by household income in college. Now for part E, we want to draw a bar graph of the conditional distribution found in part D, and in the interest of time, I've already done so. So we have our household income on our horizontal axis here, and then our relative frequency here. So I've color coded them, so the bottom quartile is in blue, second is in green, and so on. So going back to this distribution here, what we're looking at is the bottom quartile for our household income. So looking at this guy here, we have 0.327. That's going to be our relative frequency. So that's where this bar goes up to, roughly 0.327. Now, staying here in this bottom quartile, we're moving on to our second quartile here, 0.282. That'll be this bar in green. Moving on to the third quartile, 0.209. That'll be this one in orange and so on. So repeating this for the second or third, we do the same thing. Second or third quartile, looking at the bottom quartile, gives us 0.241. That'll be this guy in blue here. And then repeating this process for the remaining quartiles. And then lastly, for our top quartile for our household income, we'll do the same thing. So that's what our bar graph would look like. And then for part F, we want to write a couple of sentences explaining any relation between our household income in college and mid-career income. So to do that, we're going to go back to our conditional distribution here to kind of see what's going on. So notice people in the bottom quartile for household income in college kind of remain in the bottom quartile for current mid-career income. This is definitely a higher relative frequency than the other quartiles. So this means someone that was in the bottom quartile for household income in college generally stays there. We have a lower amount of people who go from this bottom quartile and then move to this top quartile for mid-career income. And the same can be said for our top quartile here. People who were in the top quartile for household income in college generally stayed there. We have a higher relative frequency here. They usually didn't move then to the bottom quartile. We have a very low amount here. So generally, people who were in the bottom quartile are more likely to stay there, and then people who are in the top are also more likely to stay there. So we'll write something there. So we'll say individuals in the bottom quartile are, let's say, more likely to remain there. And the same goes for people in the top. For, for individuals in the top quartile. All right, so we're jumping it to chapter 7 here, looking at section 7.1. So for this problem, we're told that the reaction time x in minutes of a certain chemical process follows a uniform probability distribution, where in minutes is going to range between 5 and 10 minutes. So we want to draw the graph of our density curve. So we're going to have density on our vertical axis, and then time on our horizontal axis. Now we know our time ranges from 5 to 10 minutes here. So when we are drawing the density curve, we are drawing a rectangle whose width is given, and in this case is 5, and whose height must be a certain value that'll make the area under the graph equal to 1. So we'll say that here. So the area under the graph must equal 1. And we know that the area of a rectangle is going to be height times width. And we know in this case the width is going to be 5. Our given interval is from 5 to 10. So that means the height must be 1 over 5. And we can check this. We know the area must be 1. If we take the height times the width, that's going to be 1 over 5 times 5. This gives us 1. So that means the height of this rectangle is going to be 1 over 5. And so the graph is going to look like this. Now, for part B, what is the probability that the reaction time is between 6 and 8 minutes? So the area under the graph of the density function over a certain area interval represents the probability of observing a value of the random variable in that interval. So what I mean for this particular example, we're looking at the probability that the reaction time is between 6 and 8 minutes. Let's actually use this graph from part A. We have 6 and 8 here, and we're trying to find this area. Okay, so the probability that the reaction time is between 6 and 8 minutes is denoted by this. And what we're going to do is just find the area of this purple region, and that'll be the probability. So we know the area of this rectangle is going to be its height, which we know is 1 over 5, times its width. Now the width of this guy is clearly 2, but we can just find that by subtracting this. So this is going to be 1 over 5 times 2, which is 2/5, which is 0.4. So that'll be the probability that our reaction time is between 6 and 8 minutes. Now, for part C, we want to find the probability that the reaction time is less than 6 minutes. So the reaction time is less than 6 minutes. So going back up to this graph here, if the reaction time is less than 6 minutes, then it must be in this region. So we need to find the area of this rectangle again, or rectangle here. And again, the height is going to be 1 over 5 of this rectangle. And so the probability is going to be 1 over 5 times the width of this rectangle here from 5 to 6. We know the width of this is going to be 1 because 6 minus 5 gives us 1. So this will be 1 over 5, which is 0.2. So that's the probability that the reaction time is less than 6 minutes, which is this rectangle. Now, for this next problem here, the heights of 10-year-old males are normally distributed with mean 55.9 inches and standard deviation of 5.7 inches. So with this, we want to draw a normal curve with the parameters labeled. So in order to do that, we're going to want to find the inflection points of this curve. So the first one is going to be the mean minus the standard deviation here, which is 50.2. And the next one is going to be the sum of these guys. So these are our inflection points. So we can use them to draw the normal curve. So the normal curve is going to look like this with our mean in the middle, this 55.9. And our inflection point to the right is going to be that 61.6, and to the left, the 50.2. So our normal curve is going to look something like this, where we have our mean and our two inflection points. Now for part B, we want to shade the region that represents the proportion of 10-year-old males who are less than 46.5 inches tall. So that's going to be to the left of this inflection point. So we'll label this. This is going to be, let's move this over, 46.5 right here. So we're going to shade the region that represents the proportion of males who are less than that tall. So let's do that in blue here. That's going to be everyone to the left of this guy. Now for part C of this problem, suppose the area under the normal curve to the left of 46.5 is given by this here. We're going to provide two different interpretations of this result. So the first, what we're going to do is essentially describe this in terms of the proportion and then in terms of the probability. So this tells us that the proportion of 10-year-old males who are less than, so to the left of this value, is given by this percentage, which would be 4.96%. So, so the proportion of 10-year-old males who are less than 46.5 inches tall is 4.96%. So we just get a percentage by multiplying this by 100. And then another way to interpret this is in terms of the probability. So the probability is 0.0496 that a randomly selected 10-year-old male is less than that 46.5 inches tall. So those are two different ways to interpret this information. Now for section 7.2, we're looking at applications of the normal distribution. So for question 38 here, we're told that the reading speed of sixth grade students is approximately normal with mean speed of 125 words per minute and a standard deviation of 24 words per minute. So for part A, we want to draw a normal model that describes the reading speed of sixth grade students. Okay. So let's do that here. We're going to have a normal model with our random variable x here. So we're going to have this normal curve. There we go. In this normal model, our mean is going to be 125 words per minute, and we need to find the inflection points. So one standard deviation to the left of this mean here, and then one standard deviation to the right. All right, so we have 101 here and 149 here. So this would be our normal curve for this situation. Now for part B, we want to find and interpret the probability that a randomly selected sixth grade student reads less than 100 words per minute. So since the reading speed of sixth grade students, this is our random variable x, is approximately normal, what we're going to do is we're going to transform our random variable x into a standard normal random variable v. And this standard normal random variable has a mean of 0 and a standard deviation of 1. So the first thing that we need to do is we're trying to find the probability that x is going to be less than 100. So we're going to take this value of our lowercase x being 100 and convert it into a z-score. So to do that, we're going to take that value of x, subtract out our mean, and divide by the standard deviation. Doing that, we're going to get 100 minus our mean of 125 divided by our standard deviation of 24. This is going to give us negative 1.04. Okay, so what we're trying to find is the area under the curve where x is equal to 100. So everything in blue here for this problem. Now, in order to find the area under this curve, we transformed our random variable x into a z-score given by negative 1.04. So this is our z-score. And since we're looking at a standard normal curve, what this looks like, when we transform x into the standard normal variable z, our curve now looks like this value is negative 1.04. And we're trying to find everything to the left of this guy. Now, in order to find everything to the left of that, we're going to look at our table that I've pasted here. So our z-score was negative 1.04. So we're going to find negative 1.0 in our column here and look for 0.04. So this is going to give us 0.1492. So that is the area under the curve to the left of 100 in this case. So that is all of this guy and this guy here. Okay, so this is our normal curve and this is our standard normal curve. So our area under the curve is given by this 0.1492 that we got from the table below. And that area is the probability that this random variable x is going to be less than 100. So the probability that a randomly selected sixth grade student reads less than 100 words per minute. Okay, so that's what's happening with the standard normal distribution here. All right, let's give another example or part C of this problem. So we want to find and interpret the probability that a randomly selected sixth grade student reads more than 140 words per minute. So again, our lowercase x here is going to be 140, and we want to transform this into a z-score. But before we do that, let's kind of visualize what's happening with our normal model here. So we have our normal random variable x, and in this case, we have our normal curve, and our x value is 140. So we want to find the area under this curve. That's going to be the probability that a randomly selected sixth grade student reads more than 140 words per minute. So let's transform this into a z-score. We know this is going to be given by this formula here. So plugging everything in, this is going to give us a z-score of 0.63. Yep. So we're going to take this z-score and find the corresponding area under the curve to the left of this. So going back to this table here, we have 0.63. So 0.6 and then this 3 here. So this is given by 0.7357. So that's the area under the curve to the left of this guy. And just so we can see with our random variable z what this looks like, this is our standard normal curve. A z-value corresponding to 0.63 is everything under the curve to the left of this 0.63. And we found that everything under the curve, this area, was given by the 0.7357 from the table. So this is 0.7357, which we found from the table below. All right, now remember, we're trying to find the probability that a randomly selected sixth grade student reads more than 140 words per minute. So this 0.7357, which also corresponds to what we have up here, is everything to the left of 140. Everything to the left of this value would be everything that's less than reading 140 words per minute. So what I mean is, we currently have the probability that x is less than 140 words, and that is given by 0.7357 from our table. That's the area under this normal curve. But what we're trying to find is the probability that a randomly selected sixth grade student reads more than 140 words per minute. So what we're going to have to do in this case is we're going to take this entire thing, which we know to be 1, and we're going to subtract out everything in blue. By doing that, we're left with everything that's in green, which is actually the probability that we're trying to find. So the probability that someone's going to read more than 140 words per minute is going to be 1 minus the probability that someone reads less than 140 words per minute. So this is going to be given by 1 minus 0.7357, which is going to give us 0.2643. So the probability that a randomly selected sixth grade student reads more than 140 words per minute is given by that there. All right, let's look at the last part of this problem here. So we want to find and interpret the probability that a randomly selected sixth grade student reads between 110 and 130 words per minute. So again, before we do anything, let's draw our normal curve here. All right, so now we're looking at an interval. Remember, for our normal random variable x, our mean was 125, and we're trying to find the probability that someone's going to read between 110 and 130 words per minute. So we're trying to find everything in this region. In this case, we have two x values. We're going to call this x sub 1. This is going to be 110, and this will be x sub 2. So we're going to need to find two corresponding z-scores. The first z-score I'll call z sub 1 is going to be given by this x sub 1 minus mu over our standard deviation, which is going to be 110 minus 125 over 24, which gives us a z-score of negative 0.63. Then our second z-score is going to be given by x sub 2 minus mu over the standard deviation, which is 130 minus 125 over 24, which gives us 0.21. Okay. So far we've found the z-scores corresponding to 110 and 130 words per minute. Now remember, what we're trying to find is the probability that x, our normal random variable, is going to be in between these guys. So everything under this normal curve, we need to find the area under this guy. Now going back to our standard normal curve here with our standard normal variable z, this looks like this here. So we have negative 0.63 and 0.21. And remember, with this distribution, the mean is going to be 0. Okay, so what's happening here, we're going to look at our table 5 and find the corresponding area to these z-scores here. So negative 0.63, we have negative 0.6, and then 3. So 0.2643. Let's do this a different color. 0.2643. And our second z-score was 0.21. So 0.21 is given by 0.5832. Okay, so these are the area under our normal curve here. So to the left of this negative 0.63 is given by 0.2643. So all of this is 0.2643. And then everything to the left of 0.21, that area is going to be 0.5832. So let's do a different color. 0.5832 is that area. Now remember, we're trying to find the area in between these guys. So in order to do that, what we're going to have to do is take the area that we see here in blue, this 0.5832, and subtract out the area that we see in green, this 0.2643. If we do that, then we're left with just the area under this curve in blue here, which is the probability that a randomly selected sixth grade student will read between 110 and 130 words per minute. So what I mean is, the probability that someone is going to read in between 110 and 130 words per minute is given by this area in blue, 0.5832, minus the area in green, 0.2643, which is going to give us 0.3189. Okay, so that is how we would do a problem like this here, looking at applications of the normal distribution.